Hello everybody, welcome back to my channel Deep Intelligence Lab. Today we'll be discussing the concept of logistic regression, which is a supervised machine learning model used for classification problems. So let's get started. Starting with the topic of logistic regression, we are given a dataset that can be represented in the form of xi, yi, where xi can be any vector of d dimension and yi can either be 0 or 1. Here 0 and 1 are two different classes. Let us visualize this graphically. In this graph, we assume that we have a single feature x and classes 0 and 1. So the points where y equals 0 lie along the x-axis and the points where y equals 1 lie above the x-axis. It is very evident that we cannot fit a straight line through these points. So something like y equals wx plus b does not help us. But notice that we can fit a curve along these points. This S-shaped curve is also called the sigmoid function. But we will come to that later. So instead of predicting the class directly, logistic regression predicts the probability of y equals 1 given x. This is also called as the conditional probability. This means that logistic regression is actually not regression in the literal sense. Therefore, each label capital Y given capital X equals X is modeled as a Bernoulli random variable with P of X probability. Now let us discuss what the Bernoulli distribution means. The Bernoulli distribution is the result of a random experiment with only two possible outcomes. Success is represented with 1, which has a probability of P. And failure is represented with a 0, which has a probability of 1 minus p. The probability mass function of a Bernoulli distribution can be represented as the probability of capital X being x equals p power x into 1 minus p whole power 1 minus x. If we had to represent this in the form of conditional probability, it would be the probability of y given capital X equals x is p of x whole power y 1 minus p of x whole power 1 minus y. This is the probabilistic interpretation of logistic regression. So logistic regression is about choosing a good functional form for p of x. We note that p of x here belongs to 0, 1, which means that p of x is a probability which is bounded between 0 and 1. Therefore, p of x cannot be modeled as a direct linear model like W transpose x, as linear models are unbounded. Now let us define something called as odds. Odds of an event can be represented as p by 1 minus p, where p is the probability of the event. If odds equals 1, it means that the probability of the event occurring is equal to the probability of the event not occurring. So if we are talking about two events, both events are equally likely. If odds is greater than 1, it means that the event is most likely to occur. And if odds is less than 1, the event is less likely to occur. This means that odds compare an event with non-event. Coming back to our original problem, probability lies between 0 and 1. This means that odds lies between 0 and infinity. But odds are multiplicative and linear models are additive. So we need a method to convert the multiplicative odds to an additive format, which can be done by taking a logarithm. So we have log of odds equals log of p by 1 minus p. And we can clearly see that log of odds belongs to minus infinity to infinity, which means this is unbounded. As discussed earlier, Linear models of the format W transpose X are unbounded as well. So we can assume that the logarithm of probability of capital Y equals 1 given capital X equals X divided by probability of capital Y equals 0 given capital X equals X equals W transpose X, which is a linear model. So putting this in a simpler format, we start with logarithm of p by 1 minus p equals z. Here z is nothing but W transpose X, but we are using z for notational ease. We can send the logarithm to the RHS by taking an exponent. So p by 1 minus p equals e power z. Since our problem was to find the value of p, we obtain p equals e power z by 1 plus e power z. And if we divide this whole value by e power z, we get 1 by 1 plus e power minus z. And this is nothing but the sigmoid function, which can be represented as sigma of z equals 1 by 1 plus e power minus z. This means that when we solve a logistic regression problem, we are actually solving for p of x equals sigma of W transpose x. Considering a binomial distribution with probabilities p and q, we have the probability of y given x and w equals p power y into q power 1 minus y. And assuming a data set with points xi and yi, we can rewrite this as probability of yi given xi and w becomes sigma of W transpose xi whole power yi into 1 minus sigma of W transpose xi whole power 1 minus yi. Here for notational ease we use W transpose xi as zi. Now we make a very important assumption that the data set xi, yi from I equals 1 to n are IID, which means the points in the data set are independently and identically distributed. So now we can write the likelihood function to be L of W equals product from I equals 1 to n P of yi given xi and w equals product from I equals 1 to n sigma zi whole power yi into 1 minus sigma zi whole power 1 minus yi, where zi equals W transpose xi. As we all know, now we take the log likelihood, which is small l of w equals log capital L of w. So we have small l of w equals summation I equals 1 to n yi log sigma of zi plus 1 minus yi into log 1 minus sigma of zi. This is called the Bernoulli log likelihood. Since we already know that the negative log likelihood is the cross-entropy loss, so we can write the loss function as L of W equals minus of sigma I equals 1 to n yi into log pi cap plus 1 minus yi into log 1 minus pi cap. Here pi cap is nothing but sigma of zi. Now let us check what the derivative of the sigma function is. We have sigma of x equals 1 by 1 plus e power minus x. This can also be written as 1 plus e power minus x whole power minus 1. Therefore, the derivative would be minus of 1 plus e power minus x whole power minus 2 into minus of e power minus x, which is nothing but e power minus x by 1 plus e power minus x whole square. Since 1 minus sigma x equals e power minus x by 1 plus e power minus x, the simplified form of the derivative would be sigma of x into 1 minus sigma of x. Therefore, to minimize the cross-entropy loss, we take its derivative, which is minus of sigma I equals 1 to n yi divided by sigma of W transpose xi minus 1 minus yi by 1 minus sigma of W transpose xi whole into sigma of W transpose Xi into 1 minus sigma of W transpose Xi into Xi. We cancel the positive and negative terms Yi into sigma of W transpose Xi. So finally we have the derivative of the loss function to be sigma I equals 1 to n sigma of W transpose Xi minus Yi into Xi. As we discussed in earlier videos, we would be using the gradient descent function to find the optimal value of W. The gradient descent update equation would be Wt plus 1 equals Wt minus eta times the derivative of the loss function, which means Wt plus 1 equals Wt minus eta times sigma I equals 1 to n sigma of W transpose Xi minus Yi into Xi. Therefore, we obtain the optimal value of W, which in turn gives us the value of P of X, which is represented as sigma of W transpose X. Hope you guys enjoyed that. In our next video, we'll be talking about the concept of support vector machines. Until then, stay tuned and don't forget to subscribe and hit the bell icon. Thank you.